All right, might as well get started. So yeah, midterm exam on the 7th. We'll do that in class. So it'll be an hour and a half. Chapters 1 through 4. I don't think we'll get to 5. We might get to a portion of 5, but we'll just see. The homework was 1 through 3. And let's just go over it real quick. So I think you were trying to determine turbulent or non-turbulent, right? So that would be the Reynolds number. What's Reynolds number equal to? Yep. So however you want to make those symbols, just make your two V's different. And remember that in the US system, you're probably going to have a diameter in feet, a flow in feet per second. And then what's the unit of viscosity? V squared per second. Yeah. So, sorry, feet squared per second, forward thinking. So that's feet times feet. Those cross and then seconds cross should be unitless. So the first one, we probably want to do something like, since we're in feet per second, right? Here, and we're inches here, so 2 feet. Velocity 6.21 feet per second. And then what's the viscosity of the fluid? 1 times 10 to the minus 5. Yep, I think so. Did it say? It didn't say anything different, right? Yeah, water flowing. What'd you get for a number? .24 times 10 to the 6. Yeah. Okay. Turbulent, laminar. Definitely turbulent. Anything over 10,000? Yeah. All right. Kind of the same process for each one. This is not velocity though, correct? No, that's flow rate. So how do we get to velocity? Yeah, Q equals A times V. So then to get to velocity, we take Q and divide by A, right? That gives us velocity. So our Q is in cubic feet per second. And our A is going to be in inches unless we convert that. So this needs to go to area in feet squared. Yeah. Anyone get that number? Just did it all. What'd you get for velocity? Say again. 4.4 feet per second. Yeah, anyone else get that number? Okay. And then same thing, right? Pump it into the equation. Is it water again? Water flowing, it says. So, yep. Goes into the Reynolds number equation. Diameter, velocity over viscosity. And what'd you get for your Reynolds number? $91,702. Yep. Yeah, so since you're comparing to 10,000, just coming up with the number and making that comparison, this is also turbulent. What'd you get for a velocity in number 3? Again, that's going to be, yeah, Q divided by A. So cubic feet per second divided by the area in feet squared. How much again, Nick? Moving pretty slow. 0.04, yeah, that's really slow per second. Q is your flow rate. So flow rate, remember, is volume per second. So flow, volume per second, cubic feet per second, velocity, feet per second. So we need velocity to plug into this creature because that's velocity. So once you get that and you have your area in feet, you can put it into this. What'd you get for the Reynolds number of 3? 1527. Feet. Sorry, unitless. So that's under the 2000, so that's laminar flow. Slowly moving along. You could, and you would just need to make that comment, like closer to turbulent, but it's kind of undefined. You just can't make that full decision. When it's between, then it's like, has a lot to do with the structure of the piping. So if it's between and there's hard 90s in there and it was kind of closer to 10,000, I would think that in the 90s it might be turbulent, then it goes laminar type of thing. So you just can't, it's one of those undefined areas.
If we're getting numbers in millions, like
Yeah.
then that's a relatively small window.
Yeah, no, that's definitely turbulent. All right, turn them in. Turn them in, turn them in. So the book heads off into energy conversations because that's how we're gonna probably solve most of our problems is by collecting the energy in and the energy out. Difference between it can be the friction, the difference between it can be the heat loss. The same amount of energy in, the same amount of energy out is pretty rare because we want to use energy to do something, either run a machine or heat a building or cool a building. Usually the energy we put into the system has a purpose, not just energy in, energy out. So we're going to define energy in some different ways. They talk about head right away, and that is energy per weight. And when we talk about energy, often in fluids, that's foot-pounds. So from statics, we know foot-pounds as a torque. But if you use foot-pounds over time, like if you say, oh, there's 50 foot-pounds of energy every second, then that torque becomes energy because it's essentially being consumed or created over time. Okay. So good thing to remember that energy is, or head is just energy over weight. Energy is going to be in foot-pounds, and that often is given. Sometimes we calculate it. And then weight is obviously in pounds. So the pounds drop out. So head becomes this thing we know as just feet of head. And you'll hear people talk about how many head, and they'll say, oh, 54 feet. So that's just a conversation of kind of energy availability in head. So the concept of head is used to describe mechanical energy that is potential and kinetic, as well as energy loss due to friction or turbulence. So that's on page 55. And then they talk about a few different heads. So this head thing, then they talk about position head, pressure head, velocity head, and head loss. So just remember, when they talk about head or when we calculate head, that is this concept of mechanical energy. All right. And there's different kinds of heads. So position head, they say potential energy per unit weight of mass of water due to the height of the water above the datum. So essentially, this has to do with weight up high. It doesn't have to be just water. If you say, oh, it's 50 feet ahead, there's something up there 50 feet, and there's a certain amount of energy that'll be tagged to that. Okay. So position head is something we call potential energy. That is our whole hydroelectric system. Massive amount of water above the turbine. We have position head. And we can calculate how much energy is in that weight up high, right? That's available energy. When they look at Bonneville Reservoir, if it's full to the top, it has all of its potential energy. If it's half full, then it has less potential energy. Pressure head describes potential energy per unit weight of mass of water due to the pressure exerted from above. So we could use, instead of the weight of all of that energy up there, we could use the discharge velocity as energy. So there's a difference there. Like if you take all this weight of water, you drop that weight, that's potential energy. You take this weight of water and put a pipe in, and then kind of venturi it down into a nozzle, then this weight creates all this pressure, right? We know how to calculate that. And then from that pressure, we get a velocity, and we can use the velocity. So it's not a lot different, like it's the same weight, right? But how we use it is potentially different. And this is more of a kinetic, right? We're going to use the motion to create the energy, not just the weight. And then velocity head describes the kinetic energy per unit weight of mass of water due to the kinetic energy resulting from its motion. So this could be, velocity head could be a number of different applications, but like a stream that maybe is turning a paddle wheel to create energy, it's drawing the energy from this moving water. And then head loss is kind of a frictional loss or turbulence. So, if this was too fast in this pipe area here, then we lose energy due to friction or turbulence. If it was turbulent, then we're losing, just eating some of our energy. If it was a really rough pipe and a really long pipe, then we're going to lose some due to friction. All right. Then we go into the conservation of mass, which I think we talked about a little bit, right? This idea of if we have a pipe and we have a mass here and it's traveling at a certain velocity, then down here, it's going to be the same amount of mass that's traveling through. If the pipe gets bigger, again, same amount of mass travels through this pipe. It's just probably going slower. And here it's going faster. So we'll talk about these different positions in a system. But the concept here is, if this is a steady flow, then the amount of mass traveling through the system is the same, regardless of the shape of the pipe. So let's just explore that a little. Let's say this is a 1/4 inch diameter, and this is a full inch. And let's say we have 0.4 cubic feet per second. So what is that? Is that a velocity? Is that a flow rate? Yeah, it's definitely a flow. 0.4 feet cubed per second. That's a volume per second. That's flow. So the question might be, since we know area 2, we know area 1, we can get velocity 1. And we can find out what velocity 2 is from the conservation of mass. It's got to be this volume, that flow rate that stays the same. The velocity's got to change because that's a bigger area. So area 1 from the 1/4 inch is going to be, I'll use pi 0.25 inches squared over 4. That's area 1. That's this area. So the question here would be, what's the velocity or what's the flow rate, right? Either one could be asked at this position 2. So A1, V1, we got to get the velocity. We have the area. How do we get velocity? We divide by the area to get velocity 1. But our units got to work out, right? So we need our area in feet squared to get a velocity in feet per second. So take the 0.4, divide by the area of 1 in feet squared. So I get a velocity of 0.003. Should do it again. Yep. Yep. And that's feet per second. So here's my area 1. Now I have velocity 1. So I got 0.0003 feet per second. Yeah. I used the 0.25, so I'm going to have to convert that. Right? I used the 0.25 diameter.
For the area that you divided the 0.4.
Yeah, that would also be the 0.25 area, because we want the velocity here, V1.
But you just did pi times 0.25 squared over 4.
Yep, and put it under 0.4.
So you just wrote this all out when those cancel?
They could, absolutely. Yep. When you multiply back by the area? Yeah. True. Yep.
So if you're given the flow instead of velocity, the area will always cancel.
So the areas to get to velocity here, yes. Probably true. At that station. Yep. Right, because I got to convert that.
Over what?
144 inches squared. Right, that's just my conversion to get rid of the inches. Just writing out this A1, V1. And then A2 is pi 1 inch over 12. There, I converted it right away because now that's in feet squared. And then we have multiplied by V2. So you get your number here. Divide by your area here, and you get your velocity too.
Got a pretty tiny number. It's supposed to be smaller than B1.
Oh, absolutely going to be smaller. Yep. So what'd you get for the number on this side? A1, V1.
$10.2 times 10 to the negative. I don't know, it's really tiny. It's a lot of zeros.
Yeah, so I got 10 to the 7. So for this, I got 1.0 times 10 to the 7 minus 7. And then what's the unit when you take area in feet squared and you multiply times velocity in feet per second, you end up with feet cubed per second, which makes sense because we know A times V is flow rate. This is pretty slow, right? Like the velocity one is 0.0003 feet per second. That's pretty slow. At 0.4 cubic feet per second, that's pretty slow. Make sure we're doing that right. So we get a different number here.
What'd you get?
24. Right? Like this should be 0.4 feet cubed per second, correct? That's what's given. And we divide by the area in feet squared.
Right, and that whole area is gonna be the pi.
Yeah, so this area, I don't know where I got this number. Maybe from somebody in here. Yeah, so this area is going to be 0.25 divided by 12. So that's 0.0208, right? That's the diameter in feet squared over 4 and pi. So that's the area. That's going to be a small number. The area is going to be really small, and we're dividing by the area, not multiplying. So this velocity goes up big time. So the area I get is squared. .0034. Well, that's maybe what this is.
That's what I got.
This is the area.
0.00034088.
Yeah, that's what I got.
Yeah, feet squared, right?
Yeah.
Yeah. Just wrote it down wrong. That gets divided into the 0.4. That's going to drive it up, right? Yeah.
What's our V1 now?
So now what's our V1? Exactly the question.
I got, I won't say it'd be wrong, but I got 73.338.
I got 24.446.
I got 1173.
Oh my gosh. Exactly. Area 1 equals 0.25 inches divided by 12, because that gives us feet, right? Feet squared, pi and 4. Oh, this is a weird camera. I hope that's, oh, that's not focus, is it? Yeah. I don't think it has a focus like button. Here, maybe we can do this. Oh. Maybe I just need to slow down here. All right.
I
Let's.
figured out why I got a different number.
Yeah, so I'm still getting 0.0003408 feet squared. Okay, so now we need to say our flow rate was what? 0.4. That was given, right? So since this is our area, we know that we can take Q divided by area to get velocity. So velocity equals Q divided by A. So 0.4 feet cubed per second divided by 0.0003408 feet squared. That'll give us a velocity in feet per second. Yeah, for sure. Over 1,000 what? Wait, for velocity?
Yeah.
0.4 divided by that?
Yeah, because that's the same as 4 divided by 0.003.
Pretty close, yeah.
4 is over 1,000 times bigger.
I got 1,173.
Yep. I think we're on the same page now. So now we know A1 V1 equals A2 V2. So in our piping system, we wanted to know what V2 was. So let's get A2. Pi 1 divided by 12 to get to feet over 4. Maybe. I got 0.001736. All right, let me do it again. Wow, calculator error. 0.00545. How's that? It's better. All right, and units? Yep. Area, square feet. So now we should be able to go A1, which was 0.4 0.0003408 feet squared times V1 1173.41756 feet per second. So A1 V1 equals A2.00545 feet per second times V2. The velocity in the second pipe.
On the left side, I think it's just 0.4.
That is.
Yep, that's what he was saying earlier.
Divide that by pi over 566.
Whoa, whoa,
Pi over
whoa.
566
Oh, yeah,
is the
you're
same
confusing
as-
it weird. Yeah.
No, it's not weird. It's the same number.
Well, you're right.
And pi, we're talking in pi numbers.
And it's easier to type in than 0.007777.
So this side comes back to 0.4, right? Whoops.
No, it's not 5
What do we get?
73.34. Velocity, so feet per second.
So for every just given flow, in one, or this is
So I think
flow of the
you guys
first
need to be careful with this. I'm not sure I agree with that number. I didn't run it. 0.4.
The second line that you wrote it, you dropped to 0, so 0.00545.
Ah, there it is. Thanks. Whoa.
And it did slow down pretty dramatically from 1,000 to.
Yeah, exactly.
Dropped to 11.
Yep. Perfect. So it makes sense, right? If we're going pretty fast in here, it's going to slow down here. So
Linear or
in steady flow, it really is. Yeah. Yeah.
So will the, if we're given flow, will the left side always equal? just
Yeah.
one?
So you recognized it right away, but remember what Q is equal to? A times V. What's this? That's Q. Yeah. So the thing is, if you're given Q, it'll fill that side. If you're given velocity, then you still have to get to Q. Yep. Absolutely. And then, of course, you could work this 3 different ways, right? 3 different variables. So if you're given 2 velocities, velocity, velocity, then you can go and you can find the necessary area. Maybe they say, okay, how big should this pipe be? We need this flow rate in this system, and we have a 1/4 inch here. How big should that be to keep the flow rate type of thing? So any of the 4 variables here can be unknown. And then it can change, the system can have 3 or 4 different diameter changes. Okay, I think you're gonna work on, let's just check those homework problems. Yeah, so you're just gonna work with, I gave you 5, 6, 7. Yeah, 5, 6, 7. So 5 is just working with Q. Oh, so then they are going to go and ask you pressure head questions. Water in a pipe has a pressure of this. What's the pressure head? Water in the pipe has a velocity of this. What's the velocity head? So you're going to have to refer back to yeah. So I guess we should talk about the conservation of energy equation also. Yeah, we did conservation of mass. We'll just slightly go into conservation of energy. So on page 56, they work through the kind of the derivation of it. You can feel free to work your way through. There are a couple things that are important in the derivation because you'll get this information coming to you differently. So it starts with the conservation of energy and it uses U and K for potential energy and kinetic energy. So U represents potential energy, K represents kinetic energy. Remember, potential is not necessarily moving. It's just a mass up high. So like a block of wood has potential energy if it's up high. If it can fall 20 feet, then that is potential energy. It's stagnant though, it's not moving, it's just potentially, right? It's there, available, we could use it or not use it. Where kinetic energy is actually the motion of a fluid that has weight. So it's actually the weight that's moving that gives you the kinetic energy, not necessarily the fluid itself. So yeah, so they will, they'll refer to U now and then, and they'll just give you U. Like they'll say the potential energy is this. So that's U. It's already been defined. So then they work through the derivation of the equation and they come up with what we're going to use as the conservation of energy for an open reservoir. So it is pretty thinly defined. So you can't use it in a lot of systems, but systems like that is where this applies. So the first variable H1 is the potential energy. The second variable is the kinetic energy available. Okay. And the way we do it is we create these two stations. This is station 1, this is station 2. And since the energy in station 1, it's got to be the same as energy in station 2, then this equation gets developed.
And those are the V1 and the V2 are squared, right?
Yeah, absolutely. V1 is squared and V2 is squared. That's how we get to kinetic energy. All right. And then the second one, the second half of the equation has pressure in it. So the kinetic energy plus the potential energy equals the potential energy, the pressure energy, and then again, the kinetic energy. So when you have, what was that, the mic? Yeah, because it goes plugged into the front. All right, so this would be like station 1, and at station 1, we just have the head, right? We have that potential energy, and then we have some kinetic energy that gets created. At station 2, then we have a different head, a different location, and then we also have pressure that gets developed. But you don't have pressure at station 1 because that's up here. That makes sense. It's down the system where you're going to get the pressure.
So H is the height.
Yeah, so what happens is the kinetic energy, the potential energy gets converted to pressure energy in the second half, right? That doesn't make any sense. It turns into that kind of energy. But the balance of energy between here and down here has got to be the same. So that's why they're equal to each other.
So that's the equation we use for one of the homework problems.
Yeah, no, you're going to just pick at parts of it, I think. So when they're asking you for the pressure head, that's this, right? If they're asking you for the potential head or the potential energy or the potential head, that's this, right? If they're asking you for the velocity head, that's this. So these are all heads. We refer to them as heads or just pieces of energy.
Since you're recording it, can you like outright say which is which?
Oh yeah, potential head is H1. I can point to it here, right?
Yeah.
Potential head is here. Velocity head. And then this is a second potential. Yeah, go ahead.
Is it just V1 that's velocity head, or is that whole number?
It's just V1 on the left. No, it's the whole number for sure. Yeah.
V1 is velocity.
So V is still just velocity.
Gotcha.
The head is the whole equation. Yep. Yep. Same with this one, right? P is still pressure, but pressure head is divided by the specific weight of the fluid. All right. So like, they're pretty simple equations. They all should create the unit of feet, right? So if you take the pressure, give me a unit of pressure.
100 PSI.
Yeah, so 100 PSI. Let's use PSF, which is pounds per foot squared, because head's gonna always be in feet. We want head to become in feet. So if we have 100 pounds per foot squared, and we divide by the specific weight of the fluid, which is what that equation says. Anyone remember the specific weight of water? 62.4. And what was the units? Pounds per foot cubed, right? So since I am recording, I should write that here. Not on the whiteboard. So just dealing with pressure head is going to be pressure divided by a specific weight of the fluid. We said we had 100 pounds per foot squared. And then we divide by the specific weight, 62.4 pounds per foot cubed, right? And when you divide by that unit down below, the unit in the denominator, it flips over, right? So this unit flips, the pounds cross, and we're left with feet. That's pressure head. What is that number? 100 divided by 62.4. 1.6. Yeah. 1.6025 feet of pressure head. So remember, head equals energy over weight. No, that is F. There should be an F in the equation. Is that correct? Okay, let me look at their notation here. Oh, they're not introducing F yet. So this doesn't have a friction loss in it yet. Where's their, oh, here we go. This doesn't have a friction loss in it yet. Right, that's the one we're looking at?
Yeah.
Yep. So then if you look a few chapters forward, we'll start to add things to the equation, right? And that is HL, not H1. So we will add this as we move along, but right now we're just going to stick with this. But if there is a friction loss, then you would add it as HL, and then there's a specific formula for calculating friction loss of a system that we'll get to. Yeah. So here's the thing that's interesting is there's gauges that measure these kind of head losses or heads. So in a system, you can go, okay, we have a potential energy here, we have a, potential energy here and a kinetic energy here, and we have certain things going on here. We work that equation that says one side equals the other. And if we calculate that through and it doesn't equal the other, then we have losses. So that can be a number of things. Like just temperature can make the system change. And of course, rusty pipes can make the system change. And then 90-degree turns can make the system change. And then turbulence can make the system change. So if we're not having the same energy out as we have energy in this kind of a system, then we have some kind of losses. Okay. All right. Definitely enough. And you have enough to work the homework now. 6, 5, 6, 7. Let me look at 7. Yeah, you're fine. You can get pressure head, velocity head. You should be good. All right. Good to go.